Hello students, here's a quick review that I'm making for exam 2, and if you really understand how these questions have been worked out, you will do very good on exam 2. This is particularly for the 8-week College Physics 1301 course. So here we go. First of all, let's consider a question where you have an object at an angle making about 20 degrees with the vertical, as you can see, and it's like a string. It's a string with an object at one end, and it's able to go around the vertical. So that's the situation. So the angle is given. Let's assume it's a 20-gram mass and the length of the string is 100 centimeters. The speed at which it goes is also given. Let it be 1.0 meter per second. So that is the situation. So the most important thing here is to understand that you have to resolve the tension in the string into its x and y components. So I have shown the tension in the string, as you can see right there. The tension in the string is this. So that is resolved into its x component and its y component. Okay? So when you do that, understand that this angle being 20 degrees, this angle will also be 20. So that makes this side the adjacent side of this triangle because this angle is 20. So that will make this t cosine of the angle, and this will make it t sine of the angle, where t is the tension in the string. Okay, I'm going to write that now. So if t is the tension in the string and that angle is assumed to be 20 degrees as given in the question, then you have t cosine 20 as the vertical component and t sine 20 as the horizontal component. The other force that you see here is the weight of the object. So you know that t sine theta is the centripetal force, which is the force towards the center of the circle, while t cosine theta is balancing the weight mg. So t cosine theta is exactly opposite to mg, while t sine theta is the centripetal force. And you have to know that this centripetal force is given by the formula mv squared by r. That's what you see there. Next, what I'm doing is I'm dividing the first equation by the second. The idea behind dividing it is to cancel the t off. You see, you can cancel the t, and then that leaves you with sine theta by cosine theta, which is actually tan theta. And on the right side, the mass cancels out, so you get v squared by rg. Now, we really do not need to do this in this particular question, but this is for any other case that may be asked. For this question, we can just go by either the first one or the second one. So let me show you. I'm using the second one. So t cosine theta is mg. Okay? I'm just rewriting that. So t cosine theta is mg, from which you can find the tension in the string. Dividing both sides by cosine theta, you will get t is equal to mg divided by cosine theta. Now, m is the mass, it's in grams, so I divided it by 1000. So 20 divided by 1000 is 0.02. That is G divided by cosine of 20. And when you put all those numbers into the calculator, you will get 0.21 Newton. Tension is force. That's how you get 0.21 Newton. I hope that is clear. That's understandable. Now, what if you're also asked to find the radius of that circular path? We can do that from equation 1. So if you're asked to find the radius, you can go with t sine theta is mass times velocity squared by radius. And make r the subject by cross multiplying. I hope you understand how that works out. R is mv squared by 2 sine theta. And then we know the mass, 0.02. The velocity is given as 1.0 squared by the tension, which we just found, times sine of 20 degrees. So when that is calculated, you get 0.28 meter per second. I mean 0.28 meter because we're looking for the radius. Now, in this question, you could have actually found the radius simply by using this right angle triangle. You could have done that since the length of the string is given. So when you do that, you will get almost the same answer, and the exact numbers won't be there because we round off the values of sine and cosine. So I hope that makes sense. Now let's go to the second question. This is one of the most important questions where you apply Newton's law to calculate the forces acting on an object moving up or down a ramp or an inclined plane. So that's what I'm trying to set up here. So that's an inclined plane. It's sloping at a certain angle to the horizontal. And you have an object kept there. And in this case, you're trying to pull the object up by applying a force. So let's assume that that force is 50 newtons. Now, if you don't apply any force and there is less friction, this object, if kept on the ramp, will come sliding down. So there are different cases. But in this particular case, a force is being applied. And look at that force. That force is actually parallel to the ramp. You notice that? It's exactly lined with the ramp. It's parallel to the ramp. So let's assume the mass of the object to be 1.0 kilogram. Now, you have to look at the forces acting on this object. This is the first force, which is the weight of the object. Remember that the weight of an object always acts vertically down. And how do you find the weight? It's mass multiplied by the acceleration due to gravity. So in this case, the mass is 1.0 kilogram. And acceleration due to gravity is 9.8 meter per second squared. So that's how we get 9.8. 1 multiplied by 9.8, okay? So that is the first force. And this is how the x and y axis are set up. The x-axis is right along the ramp, while the y-axis is perpendicular to the ramp. So we have actually rotated the x and the y-axis. Usually the x-axis is like that, right? But we have rotated it to make it along the ramp, to make the x-axis along the ramp, and that makes the y-axis perpendicular to the ramp. And that is for making it easier to solve the question. So once again, when you look at the other forces, you have to show the normal force. There should be a force that's acting perpendicular to that, which I'm going to show a little bit later. But what I've done right now is I am trying to break up the weight or resolve the weight into its x and y components. So that's the x and that's the y. So you can see that little triangle coming up here. And whatever this angle is, the same will be the angle here. And therefore, when you look at this right angle triangle, this side becomes the adjacent side, meaning it will be the cosine. While this side will be the sine. And remember, this side is the same as this. I've just drawn this here instead of drawing it here. So this is going to be sine, this is going to be cosine. Okay. So let's assume the angle to be 10 degrees, which means the x component is 9.8 sine of 10 and the y is 9.8 cosine of 10. So we got those two, one along the x and the other along the y. So now what I've drawn is the friction. Remember that friction is always opposite to the intended direction of motion. Since we are trying to pull this object up the ramp, friction is going to be down the ramp. But if the object was sliding down by itself, then the friction would have been up. Anyways, in this case, friction is opposite to the motion, and therefore it's down. That's why I've shown the friction down. Okay, that little f is the friction. Now what we got to do is find the net force along the x-axis. How many forces do we have along the x-axis? I think we got 3 forces. We got the 50 newtons. We have 9.8 sine 10. And we have friction. So since this is positive, these 2 forces would be negative. So when you take the net force, you have to, that's the net force along the x-axis, is 50, because 50 is positive, minus 9.8 sine of 10 minus the friction. But how do you find friction? Remember that the formula for friction is, it is the product of the coefficient of friction multiplied by the normal force. So mu sub k is the coefficient of friction. Let's assume that to be 0.1. All these quantities will be given in the problem. I'm just making it up as we go. And this is the normal force. It has to be perpendicular to the ramp, which means it's along the y-axis. And did you notice something? That this normal force is exactly equal and opposite to 9.8 cosine 10. How do we know that they are equal? Because this object does not move along the y-axis. It cannot. It's moving only along the x. So we know the forces on the y are equal and opposite. That's why in place of n, I'm going to put 9.8 cosine 10. 9.8 cosine of 10. So when you calculate that, you get the friction to be 0.97 newtons. And therefore we can go back and substitute everything into this equation now. And you will get 50 minus, so I just found this to be 9.8 sine 10 to be 1.70, and friction is 0.97. Okay. When you do that math, you will get 47.33 newtons. So that's the net force along the x-axis. If you have the net force along the x-axis, you can find the acceleration along the x-axis simply by dividing the force by the mass. That is Newton's second law. So the acceleration along the x-axis is 47.33 divided by the mass of the object, which is 1 kilogram, which gives the same number, of course, 47.33 meter per second squared. So that is the acceleration of the object as it is being pulled up the ramp. I hope you understood how that problem has been worked out. You may have to go over it a couple more times to understand because there are so many parts there. First, you had to look at all the forces, which is the free body diagram. You had to break it into its components. Then you had to look at the forces along the x-axis, including friction. So that's a very good question, and it's on the exam. Okay? So here is the third one. This question is made of multiple parts. First, let's just assume there is a 2.0 kilogram object suspended by a string. So that's a string, and one end of the string is attached to something like the ceiling. It's a rigid support, so it won't come down. And you have the mass at one end. And we have to find the tension in the string. Well, that is so simple because there are only two forces in this case. One is the tension up, the other is the weight of the object down. Therefore, the weight is mg. Tension, let's label it T, and mg is 2.0 times 9.8, which will be 19.6. Now, the net force along the y-axis by Newton's second law is mass times acceleration. What is the net force along the y-axis? T is up, isn't it? So positive, mg is down. So the net force is T minus mg. And since the acceleration is 0, you're going to get T minus mg is equal to 0, which gives T is equal to mg. So m is 2.0 kilogram, g is 9.8. When you substitute that, you get 19.6 newtons. That is the tension in the string. Remember that in this case, the string is just there. Nothing is happening. But in the second case, let's assume that somebody has this string in their hands and they're moving it up, giving it a certain acceleration. Now, logic should tell you that the tension in the string must increase because you're moving it against gravity. So let's find that case. So that is the case that I'm trying to show you here. It's the same mass. Okay. And so it's the same weight. That doesn't change. Now, it's moving up. As you can see, the acceleration is up. It is not 0 as in the first case. Therefore, it's the same process, the same idea. The net force along the y-axis is ma sub y, Once again, the net force along the y-axis is T minus mg, but it's not equal to 0. Instead, it's m times ay. So let's assume that the acceleration is 0.8 meter per second squared. Again, that will be given, so I'm just making it up as we go. Right, so all we got to do is now do the math. T minus, the mass is, m times g is 19.6. So, again, mass is 2.0. The acceleration on the y-axis is 0.8. So you get 1.6 on the right side. So T minus 19.6 is equal to 1.6, and therefore T is 19.6 plus 1.6. So the tension is 21.2 newtons. Now in the third case, I'm trying to say that somebody's like moving this down with an acceleration. So in this case, the tension in the string is going to be less. And by now you would have realized what's going to happen. Got to draw the diagram again and set it up, same process. So now you see that net force along the y, same thing. Once again, it's T minus mg because T is up, mg is down. But this time, since the acceleration is down, on the right side, you got to be careful. You got to put that as negative 0.8 because it's moving down. That's the difference, and that's a big difference. As a result, on the right side, you get negative 1.6. That changes the answer from 19.6 minus 1.6, and you get 18.0 Newton. So I hope that's very clear. 3 important cases. All right, let's move on to the next one. This is a particular case where you have a car taking a curve. And you would have noticed that at curves, the road is slightly inclined. So it's called banking. And there is a particular angle that it makes with the horizontal. That's called the angle of banking. Usually there is friction because there's friction all the time. But to make things simpler, we are assuming that there is no friction. And so the car is able to stay on the road just because of the banking. So look at how the free body diagram has been set up. Take a look at the forces. The weight of the car always acts vertically down. Weight of anything acts vertically down. This is the normal force. It has to be perpendicular to the road. Here's the angle of banking. The most important difference here is that we go back to how we always have the x and the y axis. See that? Which means the weight is along the y-axis. See that? The weight. It is the normal force that has to be broken up into its components, which is what is shown here. The normal force, look at this triangle. If you look at this triangle here, you'll understand that this is the adjacent side. So that's why that is cosine. And this would be the opposite side, which is shown here. Same thing, this one. And again, this angle will be the same as this. So that's why this is n cosine theta, and this is n sine theta. But it's shown here or here, same thing. So that is the force that acts as the centripetal force, because the centripetal force acts towards the center of the circle. Therefore, when you set it up, we have to assume the mass of the car. Let's just take it as 900 kilogram. Although it's going to cancel out at the end, it doesn't really matter. And theta is assumed to be 10 degrees. The radius of the curve is 60 meter. And like I said, we assume that there is no friction. Okay. So N sine theta is the centripetal force. And that's why it's equal to mv squared over r. What does N cosine theta do? It balances the weight. See that? N cosine theta is exactly equal and opposite of the weight. And this one provides the centripetal force. That's why it's set equal to mass times velocity squared by r. We got it. Now divide one by the other. Similar to what we did when we did the first question. It was the same setup. I hope you remember that. When you divide, the n's will cancel out. The mass will cancel out. And sine by cosine is tan. And you get v squared by rg. So if you're asked to find the maximum speed at which this car can take the curve, now you're able to do it. So now you can be like, okay, radius is 60, g is 9.8, tangent of the angle of banking, and you would get the number. That's the square of the velocity, so you got to take the square root, and you would get 10.2 meter per second. Now, it's clear from here that if the angle of banking was bigger, then it could have gone at a higher speed. That's why on racing tracks, the angle of banking is really big to enable them to go really fast without skidding off the road, okay? Moving on, here is the next one. We're talking about springs now. You know that all springs have a constant which is called the spring constant, and that is defined as how many newtons it takes to stretch it through a meter. So it's given by the formula K delta X. K is the spring constant, and delta X is how much it extends, stretches. So let's say that if you apply 50 newtons, this particular spring stretches through 10 centimeter. You can see 50 newtons, and it goes from that point to that point, so 10 centimeter. And if you apply 50 newtons, and the force in the spring is also going to be exactly the same. So F sub S is the force in the spring, which is the force you apply, which is 50 newtons. So putting it into the equation, 50 is K times, that's in centimeters, so I changed it into meter. 10 divided by 100 gives you 0.1. And so you're able to find the K by dividing both sides by 0.1, and you get the value of the spring constant. So the spring constant is 50 by 0.1, which is 500 Newton per meter. So let's say that you wanted to stretch the spring, and you did, and so you're actually doing work in stretching the spring, aren't you? So we're going to find the work done in stretching the spring, and also remember that whatever work you do in stretching the spring becomes its potential energy. So you get two things, work and potential energy. Let's do that. So the formula for work generally is force times displacement, but you got to be careful here. You have to take the average force because the force is changing. That's why you get 1/2 K delta X as the average force, and then times delta X, okay? So just remember that the formula for work done in stretching a spring is 1/2 K delta X squared. We got K. We know delta X is 0.1. Square it and do the math. You get 2.5 joules. Okay, so if that's the work done in stretching the spring, what's the potential energy? That is the potential energy. So Potential energy is given by the same formula, 1/2 K times delta X squared. When you do that, you will get, of course, the same thing here, because it's the same numbers. You get 2.5 joules. That's all. Moving on to the next. Now we are into rotational motion. We're going to consider a disk that is rotating. And that has a rotational inertia. And then if you put an object like a lump of clay onto it while it's rotating, we know it'll slow down. So if you're given the original angular speed, you must be able to find the final angular speed using the conservation of angular momentum. I know that's a lot, so let's do it in parts. So mass of the disk is 2 kilogram, and its radius is assumed to be 20 centimeters. Let's say it's rotating at 60 RPM. Oh, that's a problem. It's rotations per minute. Okay, we'll get to that shortly. Now, rotational inertia of a disk is mr squared by 2. That's the formula. You got to know it. So plugging those and changing the centimeter into meter, you will get the rotational inertia of the disk. The unit is kilogram meter squared. Okay. Now imagine that. Okay, let's first find the angular velocity. Angular speed is 2 pi times frequency. Now, what do you mean by frequency is the number of rotations per second. So 60 rotations per minute divided by 60 to get the rotations per second, which is what I'm doing. And you get 2 pi times that. So you get the angular velocity or angular speed as 6.28 radians per second. Now, here you see that there is a lump of clay that's thrown at 10 centimeters away from the center. So now we got to, let's find the angular momentum of the disk before the lump of clay was thrown. Because you know what? The angular momentum should be the same before and after. So let's find it. Angular momentum is given by I omega. I know I'm going a little fast. And I get the angular momentum. That's the unit. How did I get that? Because I already found the I and we know the omega. Just multiply those two. You see? I and omega. Now let me find the rotational inertia of the lump of clay. What's the formula for that? It's only mr squared because it's a particle. Mr squared. So you do that, you get 0.5. I'm assuming the mass of that clay to be 0.5. Okay. At 10 centimeters, 0.1. Yeah, that's the moment of inertia of clay. So what is the total rotational inertia of both of them? You got to add. You got to add the total to get the total inertia, rotational inertia. So that's 0.04 plus 0.005. That gives you 0.045. That is the total rotational inertia of both of them. Now, what did I say about the angular momentum? It should be the same before and after the clay is put there. So we got the new rotational inertia times, we don't know the angular speed, but we set it equal to the same angular momentum. Did you notice that? I set them equal, and then you calculate omega. So you get omega to be 5.56 rad per second. Okay, of course it slowed down. It was rotating at 6.28. Now it's gone to 5.56 radians per second. Okay, So I know you can slow this down, look at every part, try to understand. Let's move on. Oh no. What is that? Okay, I think this is the last one we're going to do. Again, rotation. Something is rotating at 10 rotations per second. And then let's say you speed it up to 20 rotations per second. And it takes 10 seconds to do that. We have to find the angular acceleration, alpha. So this is just like kinematics. It is kinematics, except that it's in rotation. So you'll have similar formulas. So the frequency is 10, again, because it's in RPM, you have to divide it by 60 to get it in rotations per second. So once you get the frequency, you find the initial angular velocity. That's why I put an omega sub naught, omega naught. And I'm going to leave it like that, 2 pi by times 10 by 60. Okay. So actually I calculated. So 1.05 radians per second. Do the same thing. Find the final angular velocity. Exactly the same process, except that instead of 10, you're going to have 20 by 60. So that will double it, and you will get the final angular speed. Once you get that, then you apply the formula for acceleration, which is alpha, is change in angular velocity divided by time. So the final minus the initial divided by the time. That's what you get, 0.105 radians per second squared. That's how you do it. Oh, there was one more question. I thought that was the last, but I set up one more question, and this is real simple but very important. Here you have a ball moving from left to right at 10 meters per second, and it's hit straight back at 20 meters per second. We got to find the force applied. Okay? So there are two things here. You have to know the definition of impulse. Impulse is given by two formulas. Impulse is the change in momentum, but impulse is also force multiplied by time. The time of contact between the bat and the ball, or whatever is hitting it. So let's take it step by step. I'm assuming that the mass of the ball is 0.1 kilogram. So very important, the initial velocity is 10 meters per second, but the final velocity is negative 20 meters per second. That's important because it's in the opposite direction. And J is the symbol for linear momentum, and it is the change in momentum. That is the change in momentum. So impulse is change in momentum. So I'm just substituting carefully. And you get minus 3.0 kilogram meter per second. So now if I give you the time, let's say the time of contact was 0.01 second, then you can use the other formula for momentum, which is F delta t. And since we know the impulse is negative 3.0, just put that equal to the force times the time, and you can find the force. Force obviously is going to be big, the force between the bat and the ball is 300 Newton. And the negative just shows that it's an opposing force. That means it's driving the ball back in the opposite direction, as we know. So these are some of the most important questions for exam 2. Take a look at it again and again, but memorization will not help because on the exam there might be subtle changes. So really understand all of these questions, and I promise you, you would do very good in exam 2. Thank you.